So we'll continue with a couple of optimization examples here. And if you haven't already done so, you might want to download the Excel file that has a lot of these examples set up. It's just called Optimization Examples. And the first one is going to be to design a cylindrical tank that holds 500 gallons of water. We make the assumption here that the top of it's going to be open and the bottom is going to be flat. So our objective is we want to minimize the amount of material that we have to use. We're assuming that the thickness is constant, so if we minimize the surface area, then we're minimizing the amount of materials that we have to use. So our variables here, we can decide what diameter it needs to be, and we can decide what height with the constraint that it holds 500 gallons. First of all, just converting 500 gallons to cubic inches, it's 115,500. Here's the equation for the volume of the cylindrical tank. It's the area pi over 4 d squared times the height. And the surface area, pi dh, is the surface of the cylindrical wall, and the flat bottom is pi over 4 d squared. So we want to minimize the surface area, subject to constraint that the volume is 115,500 cubic inches by changing the independent variables d and h. Okay, I'm going to switch over to Excel now. And you can see our equations are shown here. So I'm going to go into Data and Solver. And the area is what we're trying to minimize. So objective, minimize, by changing d and h, and now subject to the constraints. So I want to add a constraint, which takes me out of Excel, by the way, so I have to switch back over to that. The cell reference for this case is the volume, and we need to set that equal to 115,500 cubic inches. Click OK and solve. It says we found a solution, and there's our answer. Diameter 66.5 inches. The height is 33.25 inches, and you can see that the volume is exactly as we needed it to be. And here is the area that is the minimum that meets that requirement. Now, we can also look at a variation of that problem. Let me go back to the slideshow just a moment, kind of go through what we just looked at. But what if both ends had flat end caps? So I have to modify the surface area a little bit. I have to add the area of that second end cap, which just becomes a 2 in the formula as well. So go to the area, and in our equation, if I'm going to, first of all, we have pi times d times h. That's the cylindrical area, and now it'll be 2 times pi over 4 times the diameter squared. Okay. Now, nice thing about Solver is I don't have to redo everything. It's still set up to still minimize this by changing these subject to this constraint. Click Solve. In this case, we find out that the diameter and the height, at least to the tolerances that Solver set up to do, are the same. So here are our optimal shapes. If we had an open top, the diameter was twice the height. If we have a top that's the same as the bottom, that has a flat bottom and the top, then the diameter and the height ended up being the same. Now, I'm not going to go through this second example. If you want to step through it on your own, you can kind of follow the slides. But it's one where we're looking at 5 different products that a company can make. And for each product, we have a selling price, but we also have costs associated with it, of course. Machine hours, finishing hours, and the pounds of raw material. So we've put these costs in for machine hours, for skilled labor, and for raw material. And if we make the assumption that you can sell all the product it makes, what you're intended to do, of course, is to maximize your profit. So there are 5 independent variables. Those are the products we make and sell in a month. And again, going through these real quickly, these are set up in Excel already. There's your sales, and here's your cost. And again, the machine hour cost, finishing cost, raw material costs go into each one of those. So here's how that's set up in Excel. You can see if I change the volumes here, it will change the profit number here. And if we just run it without any constraints, you could see as long as we're making an infinite number of products, we make infinite profit. Well, of course, there have to be constraints on that. And so what if our machine, we've only got one, we run it for 320 hours a month. So we're running it on 2 shifts. And we have enough finishing workers that they can work up to 640 hours a month. And also, there's one product that we have a contract that we have to provide at least 20 units of that product. We'll simply add those to the constraints. So at least 20 hours of product 5. The machine hours limited to 320. Finishing hours limited to 640. And if we run that, we can see we would make 48 units of product 3, the 20 units that are required of product 5, and there is our profit, $21,000 a month. So the nice thing about setting up a problem like this is you can look at variations and say, we can work some overtime, we can work some weekends, we can increase the machine time, and we can hire enough temporary workers that the finishing hours are unlimited. But if we do that, because we're paying overtime and we're paying temporary workers, then our costs are going to go up as well. So we ask, is this worth doing? And again, by changing the constraints, so we remove the constraint on finishing hours and change the machine hour constraint to 400, you can see, yeah, it's worth doing. We actually increased the profit from $21,000 up to $23,000 a month. Okay, we will work through this one together. So we used to do, in Engineering 1016, we used to have the robots being remote controlled, and we put some objects out, and so the idea was to go pick up objects within a certain amount of time and score points. So in this case, depending on how far away the objects are, they have different point values. And so we practiced, and we know how long it takes to get each one of these objects. Time limit is 4 minutes, and so the question is, if you want to maximize your score, which objects should you get? So we want to maximize the points by changing the number of each item retrieved. And by the way, you can only get 0 or 1. There's only one of each one. And the constraint is that the time cannot exceed 4 minutes. Okay, so here's the Excel setup. This would be under the 3rd tab, example 3. And we make that a little bit smaller so we can see the whole thing. So again, let's look at Solver. And what do we want to do? We want to maximize the points by changing all of these. But obviously there are some constraints here. First constraint is that the time spent has to be less than or equal to 240 seconds. But now, as we said, we can either pick these or we don't. So we're going to add one more constraint here. I'm going to pick all of these cells, and notice in the pull down box there's one BIN, binary. When I pick binary, those values can only be 1s or 0s. And now we run it. And you can see that we can generate 325 points by picking up these. So we get a couple of the ones that are worth 100 point, a lot of them that are closer by, and our total time is just slightly less than 4 minutes. Now, if let's say, for example, that the time was increased. The time limit now, instead of being 4 minutes, let's make that 5 minutes. So we just change this to 300. Okay, and again, the nice thing is that Excel remembers all the rest of the setup. We can run it again, and in this case find we get 375, and again slightly under our limit of 5 minutes. Okay, so we went through all of those. So remember, binary lets you pick only a 1 or a 0. And again, I won't go through this next one, but it's kind of interesting from a paper called Do Dogs Know Calculus? And this guy would, on the shore of a lake, would throw a ball out into the lake, and the dog would run and get it. But Elvis, the name of the dog, would be at point A, and he wants to get to the ball at point B. And it turned out that he would not just go in a straight line path and swim out to it. He also would not do path B, which is to run along the shore, then go straight out. But he seemed to take this path C, which would be almost an optimum path because he can run a lot faster than he can swim. And so this problem just sets up to say, based on these running and swimming speeds, what is the best path? And you can do that in Excel. And it turns out to be the angle's about 80 degrees. So even if it's 30 meters down the shore, if he runs about 29 meters, then begins to swim, he's going to get there faster than that is the fastest path. And again, the conclusion of this paper was that Elvis seemed to find paths that were very close to optimal. And the conclusion also was that Elvis doesn't really know calculus. He has trouble with simple polynomials. But he did say it's an example of an uncanny way in which nature often finds optimal solutions. So if you're going to want to work through that on your own, you can. We've got one more problem to work. It's more lengthy one, and so we'll save that for the next video.